This is chapter 17, and the first problem is about loudspeakers. And it says the drawing shows a loudspeaker A and point C where listener is positioned. A second loudspeaker B is located somewhere to the right of A. They don't tell us how far. Both speakers vibrate in phase and are playing a 68.6 hertz tone. The speed of sound is 343 meters per second. What is the closest to speaker A that speaker B can be located so that the listener hears no sound? Okay, let's see. The information we got is F equals 68.6 hertz. And by the way, let's just listen to this one. So that's the website I found. And if we listen to 440 hertz, I believe that comes across. And then if we change to something, that was the C at 261 hertz, and it's way back here. 65 hertz, 69 hertz, 73 hertz. So very low tones. Okay, the speed of sound is given as 343 meters per second, as they usually do it. What is the closest to speaker A that speaker B can be located so listener hears no sound? So therefore the distance D or X is what they're looking for. I could call it either D or X. Okay, let's first look at what that actually means. Can hear no sound. I'm going to move this out of the way because I decided I do need the space here. So at point C, this is what you would hear from speaker A. I'm going to change the color there. So you get some kind of this wave here from speaker A at point C. And then at point C, I should shift this over. Actually there, that's what you hear from speaker A at point C. And then from speaker B, if I ever find the color again, undo the color, there we go. Okay, so from speaker B, you hear this. And the reason I draw it this way is because if you have trough on crest or crest on trough, then the combined superposition or interference comes out to 0, and usually in all realistic cases is close to being 0, not exactly there, but pretty much this is what you get, kind of like flat. You get very little sound, or if you're in the exact spot you get no sound at all. So that's what it means, and there's a certain geometry for which that one will work. By the way, what I drew here is of course one wavelength, and it kind of looks like we need that at some point anyway, and of course that's straightforward to calculate that wavelength. Lambda equals V over F. So when I plug in those numbers, comes out to, well, actually it comes out to exactly 5 meters, right? 343 divided by 68.6 hertz. Yep, exactly 5 meters, 3 significant figures, so 5.00 meters is the wavelength. Okay. Now, for two waves to destructively interfere, they would have to be out of phase by half a wavelength, which is actually the minimum. So they have to be out of phase by half a wavelength. They could be also out of phase at 3 half wavelengths or 5 half wavelengths, but they're asking for the closest one anyway, so that would be just 1 half wavelength out of phase, so that one of the distances from C to either speaker A or B is exactly 1 half wavelength longer than the other one. So it depends on the geometry that we have here, and I'm going to draw one line in that it doesn't show yet here. It's this line here. Okay, so that this one here is a certain distance d1, and this one here is a certain distance d2, and d2 is just that 1/2 wavelength longer than the other one. So equals 1/2 of the wavelength plus d1, and then we have destructive interference. Again, look at this here carefully. If d2 is just that 1/2 wavelength longer than d1, then we will have crest on trough. Okay, so therefore 1/2 wavelength equals d2 minus d1. In the meantime, lambda is being given, so and d1 is given as well. All right, it's 1 meter, 1.00 meter here in the problem. So therefore, the way I actually should write it is just like this one here. So I have d2 equals 1/2 times the wavelength, which is 5.00 meters, plus 1.00 meters. And that comes out, let's see, this 2.5 plus 1 is 3.5. So therefore, I know that this one here is 3.5 meters long. This one here is 1 meter long. So this one is half a wavelength longer, 2.5 meters. And then I have to figure out what this distance is. Okay, so from the geometry, I should figure therefore out what d is. And because I put so much information in here, I think I'm just going to copy this one and draw a little bit again here. So again, I need this one line there. There we go. There we go. Okay. Here it's a little bit deceiving that this one here looks like a right angle. It's not. It's not given in the problem as a right angle. I don't know if it is or not. In any case, I cannot use it. What I'm going to write here is now that this one here is 3.5 meters and this one here is given as 1.0 meters, and again this is what I'm supposed to figure out. Okay, now here's a little bit that helps if you know the geometry of triangles. I'm going to draw this line in here, and now I can figure out the following. Let me move this one here just slightly out of the way, put it perhaps there. Given the 1.0 here, I can easily figure out what this one is, x1 I call it, which means I use the sine of 60 degrees. And yeah, and I can figure out what x1 is. Then I said before, this is not a right triangle, it only looks like it, so I don't know what this angle is, so unfortunately I also have to figure out what the y is, and once I have the y, I can figure out what this x2 is here, and therefore the distance. So overall, it actually becomes quite a complicated geometrical problem, but in any case, here it is. The x1 divided by the hypotenuse, it's not the sine, it's a cosine, I'm sorry, x1 over 1.0 equals the cosine of 60 degrees, respectively x1 equals 1.0 times cosine of 60 degrees. Cosine of 60 degrees is exactly 1/2, so I'm going to come up with 0.500 meters. Of course, 1/2 times 1.0. I have to figure out what the y is, and for that I use the Pythagorean, where I have 1.0 squared minus 0.5 squared. Take the square root, and that comes out to the square root of 0.75, which is 0.866. That one actually I could have done over the sine. Sine of 60 degrees is also 0.866. So that's what y is. And then in order to figure that x2 out, I can again use the Pythagorean in this part of the triangle. So x2 equals 3.5 squared. That was supposed to be a 3. Whoa. 3.5 squared minus that 0.866 squared. Take the square root. And I'm going to come up with, let's see, so it's 3.5 squared minus 0.866 squared is 0.75. It's 11.5, and then I have to take the square root of that, and I come up with 3.39 meters. So the overall distance d equals 0.500 meters plus 3.39 meters is, of course, 3.89 meters, roughly 12 feet. They have to be apart from each other so that we have destructive interference. Real world application of it is a concert hall where you're getting the sound waves from any kind of instruments, and then depending on the frequencies that the instruments are playing, depending on where you're sitting, depending on where the instruments are located in the orchestra, you actually do get one or the other note that you just cannot hear because you're sitting at right that spot where that particular note experiences destructive interference. This problem is about beats. So it says two pure tones are sounded together. The drawing shows the pressure variations of the two sound waves measured with respect to atmospheric pressure. What is the beat frequency? So they're asking for the f of the beat, and as you can see in the text, the beat frequency is f1 minus f2, and it's easy to figure out what f1 is. It's 1 over the period, so divide that by 0.02 seconds, and then f2 here is 1 over t2, which is 0.024 seconds, and perhaps I could have written this one here. So it's just a matter of plugging in the seconds that are given, and you come up with the beat frequency, which is also going to be in hertz. And then, of course, what that answer means is that you have here a certain frequency, and then here one that is just slightly off, and when you combine the two and you listen to those two, you get that beat frequency, which kind of tells you from here to here. That would be half a cycle. Respectively, these two here is 1 full cycle, where the two combined here kind of raise and lower in their loudness due to the beat frequency.